Oh, wait. Wow, we got some people here today.
Sir, I had a quick question. We
Yes,
didn't do the R4 and R6, right? That's what that circle is right there.
that's right. Pretty much all the homework for the last few sections I've been giving in class. Everything here.
Which one was the one in red?
Which was the homework?
Yes, that you gave us. The one that you sent out.
Yeah, it was like two different little sheets that had problems on them.
You said to do the odd ones.
Yeah, I said try the odd ones.
Yeah.
And then for the rational functions, I had given you some problems to do. And then there was one problem at the end of class from last time. So
Test is on Wednesday, right?
well, that's what we're going to talk about.
Okay.
See, yeah, it's 1 o'clock. Okay, everyone. So let's do a well, hello. Hope you had a good weekend. Blah blah blah. Our schedule says that we're supposed to have a test on Wednesday, and normally I send out a review the week before, so you have the weekend to study. I didn't do that. Nobody emailed me either. So we have an option. We can keep this test on Wednesday. I have no problem doing that. It'll cover only material up through last week, which will be rational functions. What we do today will not be on the test. But we come through and I give you a review later on today, and then you'd have a couple of days, a day or two with it. The other option is to move this test to the following Monday. Would that be the 20? Wait a minute, hold on. Yeah, today's the 18th. So we would have to move it till the 26th. Just make sure those dates are right. Yeah. That's the wrong date, isn't it? 25th. Sorry, 25th. So let's just do a quick vote. Oh, if we do the 25th, today's material would be on the test. Today's would, but it would not. What we do on Wednesday would not be on the test. So two choices. Keep it on Wednesday. That's in 2 days, with material only going up through rational functions from last week, or move it till next Monday. I'll send you a review. Either way, I'll send you a review in the next today, probably. Any questions before we take a little vote here? Do you want to talk to each other about it, or? Okay. You have a question? What do you got? Well, 5.4, I don't think is confusing at all, because it's basically, if you can do the graphing of the rational functions, 5.4 you should have no problem with at all. In other words, if you're okay with polynomials and rational functions and how we've been setting them equal to 0, then you should have no issues with 5.4. Now, 6.1, okay, if we get to that, which I intend that we would get to some of that, I wouldn't say it's confusing, but it is new material. It's newer material. It's not tied into anything we've done. So, but there wouldn't be a ton of it on the test. There'd just be a little bit of it. So, does that answer your question? Okay. What do y'all think? What are you feeling? Keep it on Wednesday? Move to Monday? Okay, all right. So it looks like we have a majority that wants to move to Monday. How about at home? Do y'all care?
It doesn't matter.
doesn't matter.
Doesn't matter? Okay. Let's move it to Monday, all right? Move it to Monday. I'll send out a review. That'll give me an extra day to get a review together. So I'll send out a review by tomorrow. And then that test will be on Monday. All right? All right, so let's get down to first this problem that I sent you home with, right? It was the only thing I wanted you to really look at, right? Was this? So I wanted you to graph this following the steps that we learned in class. So I'm not going to go through this like every little detail. I'm going to actually ask you to tell me what happens. So what is the first step for this? Can someone tell me what the first step is and what they got? What do we do first? Factor everything out. That's hard, right? I mean, you got to do, for each one of those, you had to do like a synthetic division and come up with your list, blah, blah, blah. So who wants to give me the numerator factored, the top factored, what they got?
X plus 3 and x squared minus 4, or x plus 2,
X plus 2, x minus 2? Okay, so that work is not being shown, but this numerator factors to be this. Do we have anybody that agrees? Yes, agree? Okay, so we'll go with that. And then how about the denominator? Someone got the denominator? X minus 5 squared, and then you said times what? X plus 3. Anybody else get that?
and also an x times x.
Oh, and an X in here. I'm sorry, I didn't hear you if you said that. So y'all in agreement with this? So you had a double. If you did you do the synthetic? I'm just curious. You probably got it to work when you tried -3 first, right?
For the denominator,
Oh, does it go with grouping or something? Oh, sorry. So you didn't need the synthetic for it? Okay. All right, so look, I'm not going to go through those steps right now, okay? If that's something where you're like, I don't know how to do this step, then you'll need to get with me or go back and watch the lectures or whatever, tutoring. Say again? For the denominator, yes, okay. Yeah, not for the numerator is grouping. But you can also do it with synthetic. So, I mean, synthetic's kind of like, it's going to work. If it works by grouping, it'll also work by synthetic. All right, okay, I agree. This looks good. So the first step was to factor. Why do you always want to factor first? Yeah, make sure there aren't any holes in the graph. And holes would happen if any of these factors are the same. And we actually do have factors that are in common. These two factors in yellow will cancel each other out. But before we cancel them out, we need to make a note to ourselves. We are going to have a hole in our graph. Where? At x equals -3. So when we go to graph this on the x-axis at -3, when we look up and down, we should see a hole there, all right? So we cancel those factors. Now, the second step, what's step 2 of the process? X-intercepts. And for that, we set the numerator equal to 0, right? And you only have to set the things that are left equal to 0. You don't set the x plus 3 to 0. So you set that equal to 0. Again, I'm not going to show the work. We should just get two answers, 2 and -2. Those are going to be points on our graph. The third step is the vertical asymptotes. For that, you set the denominator equal to 0. And we have one solution at 5 and the other one at 0. Those are your vertical barriers, right? The fourth step was what? The horizontals, right? Horizontal asymptotes, HAs. So this is where you compare the degrees, right? You look at the degree of the numerator, which was 3. You look at the degree of the denominator, which was 4. You compare them. In this case, the top one is smaller than the bottom one. And what happens whenever the top is bigger than the small? Top one is smaller than the bottom one. No, there is. If it was the other way around, it would be none. If it was 4 on top, the x-axis, y equals 0, the x-axis. So on the test a week from today, I am going to allow you to create a reference sheet for the test. So you'll be able to have one 8.5 by 11 sheet of paper. You can put any formulas, any steps, anything that you think would help. What you cannot have on it, though, is just worked out problems. So if you want to write down all the steps to graph a rational function, write them all down, all the steps to do a polynomial, all the stuff to do a quadratic, whatever you want. But just don't work problems out, all right? Synthetic division, same thing. You can kind of tell yourself how to do it, but you can't actually work out a synthetic division. So when it comes to these horizontals, I'm saying that because when it comes to these horizontals, I gave you a set of steps on how to do it, right? Last class. Where is it? Where is it? I know it's here. Here we go. For the horizontals, you compare degree of numerator and denominator. You have these 3 cases. Was there a question, Amanda?
Just about the horizontal degrees, when it's 3/4 and it's, I guess, a larger number on the bottom.
That would be this case right here. If the numerator's degree is smaller than the denominators, because we had a 3 and a 4, right? Then in this case, the x-axis is the horizontal asymptote. Now, the x-axis is the same as y equals 0. The line y equals 0 is the x-axis. What you were saying was the other way was number 2. If it was the other way around, if the top was bigger than the bottom, then we wouldn't have any. Then the left and right sides either go up or down. And then when they're equal is that one special case where you have to look at the numbers in front. The coefficients, yep. Okay, so where are we here? Yeah, okay, so we're here. Now, what do we do? Step 5. Sketch it, right? Put all this information on a picture. All right, so here comes my sketch. I'm going to draw my x-axis, my y-axis. I'm going to draw the graph in blue. So my x-intercepts are at 2 and -2. Those are actual points on my graph. I have vertical asymptotes at 0 and 5. I'm going to draw those with dotted lines. I'm going to use green here. At 5, it's kind of easy to do. 5, I can do my dotted line. At 0, I told you it's hard to draw through a solid line, so I'll just put kind of like dashes that are kind of tilted a little bit. That way you can see it. And then you can extend it up here if you want, down here. Okay, 2 vertical asymptotes. The x-axis is our horizontal, so that means out on the edges only, I have dotted lines that are going to act like magnets and pull my function towards it. And that's all the information I have. And the hole, don't forget the hole. We do have a hole, right? But I'll get that in the final picture. Now I need what? Test points, right? How many should I have? Yeah. Do you remember I said count how many x-intercepts you have? I have 2 x-intercepts. I have 2 verticals. You'll always have one more than the sum of those 2. So I should have 5 test points. That's what I will need to graph this, 5 test points. So I heard on the edges, so something to the left of -2. Did someone pick something to the left of -2? -4. When you plug -4 into the function, did you get a positive or negative number out? Oh, you haven't done it? Okay. Caught you. Okay, -4. What? It's negative. So does everyone understand what you have to do there? Take that -4, plug it into the original function. You can plug it into here or here. I like plugging it in here because it's easier to figure out what the sign is. Let's just try it. If I plug -4 in right here, I get a negative number, right? -4 right here, I get -4 minus 2, it's -6. So 2 negatives would multiply to be positive. Then on the bottom, if I put -4 here, -4 minus 5 would be -9. Square it, that's positive. But then right here, I have a -4 again. So a positive and a negative will give me negative. Positive on top, negative on bottom gives you negative. Yes.
What happens if the denominator is 0?
Well, okay, so if you had plugged in your test point and you got the denominator 0, I would at that point panic because you should have already accounted for that, right? When you set the bottom equal to 0, which means you missed it earlier. Your test point should never cause you to be undefined, and your test point should never cause the top to be 0. Does that make sense? Your test point should be somewhere else. Good question. So when we plug in -4, I get a negative number. So I'm going to put a blue dot here below it. Remember I said I don't care how far down you put it, as long as it's below the x-axis. Now we have to plug in another test point, something like -1. And when we plug that in, you should get a positive. I'm not going to show that. You should get a positive here. What would be another good test point? Where else do we need information? 3 would, right? We need one at 3. Where else? 6. Okay, we're missing one. At 1. Let me try and verbally explain the test points to you. You should have a test point in between every x-intercept and vertical asymptote that you have, and on the edges. So like here I have an x-intercept and a vertical, right? X-intercept, vertical. I should have something in between. Here I have a vertical and an x-intercept. I should have something between. Here I have an x-intercept and a vertical. I need something in between. And then on the edges, you always need 1. Okay? If you had 2 x-intercepts next to each other, you would need something between. If you had 2 verticals next to one another, you need something between. All right, so what happens? If we plug in 1, I believe we get a negative number. If we plug in 3, we should get a positive. And when we plug in 6, we actually get positive again. So somebody who actually did this problem, do you all agree with me? Is this what you were getting? Now it's time to draw the picture. So I always like to start with the leftmost point. I'm going to draw it to the left, and then I see there's a magnet there. So I'm going to have to curve up towards that magnet. When I draw to the right, I'm back in kindergarten. I'm going to go connect the dots, and then when I draw to the right, I've got my vertical in my way. It's going to force me up. So it's going to look something like this. We talked about last class why that can't go down, right? On that vertical right here, it went up. It couldn't go down because you created an x-intercept, right? Can't do that. Then over here, I jump to this point. I draw it to the left. Vertical is going to force me up or down. Have to go down, right? Can't cross the x-axis here. So I'm going to have to go down, connect, kindergarten, 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 and then here, forced up. Go to this dot to the left, it forces me up, and then to the right, I have to flatten out towards the magnet. So it's going to look something like that. You have to imagine that the next test can't be that long, right? In terms of, I can't ask you to do a lot of problems. Would you agree? I mean, because, let's see, did our last test have quadratics? I don't recall. It seems like it's been so long since we did the last test. Let me just look real quick. Yeah, so we did one type of quadratic here. No, this was a bonus. So yeah, think about what this next exam is going to have on it, right? It's got quadratic functions, polynomial functions, rational functions, sketching those. So quadratics, that's a whole set of steps, right? Polynomial, same thing. You might need synthetic division. Rational functions, same thing. So I can't make this like a 20-question test. It's really going to be probably closer to like 6 problems, maybe 7, because they take a little time. Just keep that in mind. There you go. There's the picture. Any questions? All right. Okay, so today, what are we doing today? I thought I had already set this up. 10:18. So the first part of today, like I said, is gonna flow very nicely with what we've already been talking about. We want to look at now solving polynomial and rational inequalities. So let me remind you of inequalities and what we already know how to do. All right. So we have seen first linear inequalities. As an example, if I ask you to solve negative 4x minus 12 less than 18. This is a linear inequality, right? It's linear because you see x is the only variable there and it's raised to the first power, right? And it's an inequality because you have this symbol instead of an equal sign. And the way we solve these when we were talking about them earlier this semester is that these are the easiest to do because you basically treat them like you do linear equations. You just isolate x by itself. The only tricky part is if you ever multiply or divide by a negative number, you have to flip the inequality over. That was the only kind of like danger zone with this. So to solve this, add 12, you get negative 4x less than 30. And then I'm going to solve for x. So in order to get that negative 4 out of there, I have to divide both sides by negative 4, which means I will have to flip the inequality over. So I divide by negative 4, divide by negative 4. This becomes x greater than, and then that right there, we can reduce the fraction, negative 15 over 2. That's how we solve linear inequalities. There's not a whole lot of tricky stuff to it. How about the quadratics? That was the next thing we looked at. For quadratics, something like this. Do you remember what I did to solve something like that? That's a quadratic. It's an inequality because it says less than or equal to 0 here. Remember the steps? What do? First, set it equal to 0. And then once you get it equal to 0, let's do that. We're going to set it equal to 0 first. Then you try and factor or use a quadratic formula to solve this. In this case, I believe it factors x minus 8 plus 6. And you have two solutions, 8 and negative 6. Okay, so once we do that, now what? We set it equal to 0, right? We set it equal to 0 first. Then what do? You do a number line, right? And you do a number line, you say, oh, okay, once I have my number line here, I put negative 6 here and I put 8 here. And then we did test points, right? Test points. Well, I would have 3 test points here, here, and here. And where do we plug those test points in? The original inequality, and we see if it's true or false. So if I plug this in, I could test maybe negative 7, 0, maybe 10. And if I plug those into this, what will happen is I will get that if you plug in negative 7, it will not be true. Okay, this will not be true. If you plug in 0, check for yourself, 0 here, 0 here, you get negative 48 is less than 0. That will work. And then 10 won't work. And so your answers are everything between negative 6 and 8. And would we include negative 6 and 8? In this case, yes, because we wanted to know it was less than or equal to 0. We know it's equal to 0 at these 2 points. So our solutions would be negative 6 and 8 and everything in between. So it would look something like this. Bracket negative 6 to 8 closed bracket like that. That would be where this inequality is true. Right? So there's more involved for a quadratic, isn't there, than there is a linear? Well, now we just want to talk about polynomial and rational inequalities, which we pretty much need to be able to do the same thing we kind of did with the quadratic, because a quadratic is a polynomial. We need to figure out where it's equal to 0 and then do these test points. So this is very much tied into what we've already kind of done. Let's see if we can do it. How about this? So this is the new stuff for today. The new stuff, how about let's do a polynomial inequality. And as your first example, let's do 3x to the 4th minus 27x squared greater than 0. I'd like to know when that is greater than 0, right? So here's what I'm going to do. I'm going to recognize that the left side of this is a polynomial, right? We could almost look at it like a function, f of x equals 3x to the 4th minus 27x squared. And if I asked you to graph that, you have a way of doing it, don't you? I'm going to move extremely fast through this now because this is something we've done. If I were to graph this, I could tell you right now that the left and right-hand sides would have to go up. In the middle, I don't know. And that's because it's an even power and a positive leading coefficient. The next thing I could tell you is where the x-intercepts are. I can tell you where this thing equals 0. And to do that, I would set it equal to 0, right? So I'm going to set this equal to 0. And I'm going to factor out a 3x squared, which leaves me with an x squared minus 9. And that's a difference of squares. So I have 3x squared times x plus 3x minus 3 equals 0. That means I have 3 x-intercepts, right? At 0, 3, and negative 3. at 0, 3, and -3. I know that if I graph this, it would go through those points, right? I can also tell you what happens at each of these points, whether or not I cross or bounce. What would I do at 0? 0 comes from this one, right? 0 comes from here, -3 and 3. What do I do? Bounce. I bounce because it comes from x squared. So now I'm going to bounce there and I'm going to cross at these two. So if I were to draw this, because the left side goes up, right side goes up, I know that I'm going to come through and cross, bounce, cross, and go through, right? So what was the original inequality asking? When is this thing bigger than 0, right? Greater than 0 would correspond to where is this graph above the x-axis, which is happening here and here, right? Those two are the places where it's happening, which corresponds to everything to the right of 3, everything to the left of -3. What about 3 and -3 it's themselves? Do we include these points or not? No, because we want it to be strictly greater than 0. We don't want it to be equal. So I do not want to include 3 and -3. So the way I'd write that is -infinity to -3 with a parenthesis, unioned 3 on forever. This problem would be very difficult to do if you didn't know how to sketch a polynomial function quickly, right? Are there questions? No? Is there a question? Yes. Go ahead.
Is it, so it's basically, like a quadratic, like you're able to write a parabola between 2 points. So you, like with a quadratic, you can do the same thing with this, right? And just see what's underneath the x-axis. It's asking for what's left.
Yeah, so if this was asking us, when is this less than 0, right? Then I would have to be looking at this in this region, right? Now, I would not include 0 in the endpoints if I were saying less than 0, right? It would have to be 2 intervals, -3 to 0, union 0 to 3 with parentheses on everything. That make sense? So if we know the graph, we can pretty much answer any inequality, any inequality that's being asked, right? If we know what the graph looks like. Go ahead.
I was saying, so the 3x to fourth,
Uh-huh.
we change it to 3x to 3x cubed.
Yeah.
It would have been down and then up to the ending, right?
Well, let's see. Let's do it. It wouldn't take us that long to do, I don't think. 3x cubed minus 27x squared. Do you want to still stick with greater than 0? You want to do something different? Greater, stick with it? Greater than 0. So here's what I would do. I'd say I look at the left side like a polynomial. It's an odd power positive leading coefficient. That means left side down, right side up, right? Now, we need to figure out where it actually hits 0. So I set it equal to 0. Factor out a 3x squared. This time I don't get x squared minus 9, I just get x minus 9, don't I? And so I'm only going to have one answer there, right? This is going to give me 0, and this one's going to give me 9. So I only have 2 x-intercepts. So 0 here and 9 here. I know that the right side, left side goes down. I know the right side goes up. And let's see, what's happening at 0? Bounce or cross? Bounce, because it comes from x squared. And then 9, we're going to cross because it comes from a first power on that. So cross here. So we're going to bounce off. Bam. And then we're going to cross through here. So if I wanted to know where it was greater than 0, it would just be whenever we're bigger than 9. So this would be from 9 to infinity. Not including 9, right? Because if we plug in 9, we get 0. So we want to be strictly greater than 9. Give me any number bigger than 9, and I promise when you plug it in here, it'll be true. Give me anything less than 9, it's not going to work. This make sense, everyone? Okay, so what about a rational inequality? How would we go about that? Well, we have to be careful. Oh, you know what? I just remembered something. No one caught me on it. We never put our hole. Did we? We were supposed to have a hole at -3. Go back to this. Remember at -3, we're supposed to have a hole, -3. So what you need to do here is put a hole here. And that means you might need to, I don't know what made me think of that, but let me see here. I can't see what the hell these colors are. No. There's no built-in white pen anywhere. Okay. Well, that's a hole there. If you have an eraser, you can just erase. Let me see if I can erase this way. There we go. Now we have a hole. Sorry about that. I even said it like right before I put it in there because I didn't want to forget it. But I did. Okay, so for a rational function, let's take, but sorry, not a rational function. For a rational inequality, here's what you do. Let's say we have something like this. X cubed minus 4x over x squared minus I'll make sure this works. I'd like to know when that is less than or equal to 0. Well, I have bad news. I mean, we basically have to look at that as a function and figure out what its graph looks like. And then we can look anywhere it's below or equal to the x-axis, which means you have to go through all the steps to graph it. So on a test, I mean, it's very likely that, you know, I could just ask you one of these and it's kind of, you're going to have to do the other part anyway, kind of, right? So you have to go through the whole set of steps, factor everything out, right? So we treat this like a function. We factor it, let's see, we factor the numerator, we pull out an x on top. We get x squared minus 4. That'll factor some more. On the bottom, we get minus 6 plus 5. This will go even further, plus 2 minus 2. Linear inequalities are great. Quadratic inequalities, not so good. Polynomial inequalities, rational inequalities really suck because you just got to do a lot of work. There's no easy way to do it. Not if you want to be precise and get it right. You have to go through the whole thing. So let's see how quickly I can go through this. I have x-intercepts where? 0 plus or minus 2. So I know with this graph right now that at 0, I have an x-intercept. I'll do it in red. At 2, I have an x-intercept. At -2, I have an x-intercept. Okay. How about verticals? -5 and 6. So at -5, over here, we've got a vertical. 6, I've got a vertical. All right. How about horizontal? Look at the degrees here.
No.
There are none, which means the left and right-hand sides either go up and or down forever. All right, so that's all I've got. Well, test points, right? Well, when we do our test points, this is pretty much going to answer the question for us, because when we do our test points, we're going to know whether or not we're above or below as we do it. So what sucks is we're going to have 6 test points. We need something over here, -6, -3, -1. 1, 3, 7. Jeez. I'll give you a little hint here to use at your own risk, okay? If every factor you have here is to the first power, then as soon as you find one of these, they will alternate the rest of the way. Okay, so like if this first one turns out to be positive, then it'll be negative, positive, negative, positive, negative, positive, negative, positive. It's when you have like squared that things will, it's almost like, remember like the bouncing and the crossing? It's kind of the same idea. It gets real tricky though when you have multiple things squared. So I don't want to have to test all these, but you know, that's what you would have to do. Let's do the -6, or let's do the 7. Let's do the 7. 7 in here, positive, 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 positive. So if we plug 7 in, everything's positive. So we would be above. If you plug in 3, positive, 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 negative, positive. So you're going to wind up with a negative there. If you plug in 1, you're going to get positive, positive, negative, negative, positive. I know I'm going through that quick, but you understand what I'm doing. Just kind of a quick check of these. Positive there. Plug in -1, that's tricky. Negative, positive, negative, so that's positive. Negative, positive, so that's negative. So positive and negative, negative. So down. I won't do the rest. Up and then down. Kind of a weird looking graph here. I'm going to draw it because we may as well. All right. Look at the far left point. I have to go out to the left. Do I have a magnet? No. Should I go up? It's either going to go down or up. Down. Why not up? You'll create an x-intercept that doesn't exist. It has to go down. So it's going to go down on the left. How about if I draw it to the right? Barrier, right? That's going to force me down. So it's real weird. It's going to almost look like a little U over here. Does that. Go to this point. To the left, what happens? Up. To the right. Yeah, we got to go down, down, back up through here, here, back down, through here, and then we get to here, barrier is going to force me down. It's kind of a fun one here in the middle. It goes up here, goes back through, down, goes back up, almost like a little polynomial here, back and forth, and then down through here and down. On the right side, if I go to the left, it's going to go up. If I go to the right, it's got to go up again because it can't come down and cross through the x-axis. So it looks kind of like the bottom left-hand corner looks, but it's going this direction instead, up instead of down. Now, we haven't answered the question. Are there any questions on the picture, though? All right. And
The magnets on the side,
there weren't any?
yes, and why is it?
Because the degree of the numerator, 3, was bigger than 2. And so when there's no horizontal, Amanda, that means at the ends, it's either going to go up or down. So the reason it went up over here, when I was drawing it to the right, the reason it went up and not down is because if I went down, I would have to cross the x-axis. And these 3 points are the only places I'm supposed to cross. Make sense? It's like a process of elimination. It's like you can't go down, you have to go up.
So if that was a 2 on the top and a three on the bottom, we would have.
then you would have the x-axis would be your horizontal. Mhm. All right, so now let's answer this question. When is this thing less than or equal to 0? So we're looking for anywhere where this graph is either below or touching the x-axis. So that's going to happen here, it's below, right? Between here and here, it's below. And then over here, it's below, right? Those are 3 intervals. That's everything over here forever, everything between here and here, and everything from here to here. 3 intervals. How would I state that? How would I say everything to the left of 5? You get an infinity to -5. Do I include -5? No, because the graph, we're not even defined at -5, right? But it goes all the way up as close as you can get. Union. Now, how about this piece right here? -2 to 0. Do I include -2 and 0? Yes, this time, yes, because there was an equal sign and my graph actually does touch the x-axis there. So bracket -2 to 0, right? -2 to 0. And then another place from 2 all the way to 6. Do I include 2? Yes. Do I include 6? No, can't include 6. There you go. So a lot of, anytime, like in calculus, you'll be doing a problem and you'll get to this point and you'll be like, okay, I need to know where this is greater than 0. And so when you're looking to see when it's greater than 0, you look at it and say, oh, okay, is it linear? Is it quadratic? Is it polynomial? Is it a rational function? And if it turns out that you have a rational function, you want to know when it's greater than 0, you're going to have to do a bunch of work. Okay. So that's why we do it here. We want to make sure that we know how to do it, that when we get to calculus, we're not like, I don't know how to solve inequalities. That's pretty much it for this, though. Okay. Do y'all see there's really not anything new other than the fact that at the end you have to look at your graph and see, like, when is it below or above? No? Okay. All right, all right. Let's do this. Trying to think of how I want to do this. How about this one? I want you to see if y'all can't maybe talk to each other, work together, see if you can't figure out how to go about this. I'll give you a few minutes to work on it. This is an interesting problem, depending on how you go about it. Tavi, I don't know when you sent that six, is that what you're saying for this one, Tavi? What you put in the chat? What are y'all doing? You know, getting anywhere?
So it can include 5.
How do you mean? Do what?
X can be 5.
X can't be 5, is that what you have? Anything else works, or you're just saying X can't be 5, like for sure?
Well, yeah, because then the denominator would be 0.
Yeah, the denominator would be 0. I agree. We know that right off the bat, X can't be 5. But what could it be? Can it be anything else? So look, what if I had given you this problem? That problem there. The left-hand side of this is a rational function, right? And then you could just say, okay, what makes the top 0? -1, right? What makes the bottom 0? 5. And you'd be pretty much doing what we did on the previous problem. But that's because the left-hand side is a rational function greater than or equal 0. I've thrown a kind of curveball in here by putting this -1 in here. This -1 is causing some issues, right?
Yes.
Yeah. So there's different ways to approach this. I'm just curious to see who did what, and maybe we'll see if that road goes anywhere. So
I subtracted from X plus 1, I subtracted X minus 5.
what do you mean subtracted from it?
Because the 1 can be taken as an X minus 5 over X minus 5.
Oh, you got a common denominator. Okay, I like that. So instead of writing this as a 1, let's write it as X plus 1 over X minus 5 minus X minus 5 over X minus 5, greater than or equal to 0, right? That's the same thing, except rewriting the 1. I like this idea because what it does is it puts these together into a single fraction. And now we can subtract. So be careful on that subtraction. You have to do minus X minus 5. That'll be over the common denominator, which is now X minus 5, greater than or equal to 0. And what do you get on top? 6. 6 over X minus 5, right? Greater than or equal to 0. So that algebra, look what it did. It allowed us to get a rational function. This is a rational function now. And so now we can just play the game that we were playing before. We just go through, can we graph that? Let's see how fast we can graph that. Do we have any x-intercepts? No, why not? Yeah, there's nothing you can do to make the numerator 0, right? So there are no x-intercepts. Because remember, the first step to graph a rational function is to set the, well, after you cancel the factors, is to see if there's anything that makes top 0. So we have no x-intercepts. We have a vertical where? 5, or yeah, at 5. So I know I have a vertical at 5. And horizontal asymptote? The x-axis, because the degree on top is smaller than the bottom. There is no x here, right? So that's like x to the 0, x to the 1. So we know it flattens out like this. I realize I'm kind of going through this kind of quickly, and I'm not writing down a lot of details on how I'm drawing this picture. But this is kind of the idea when you get to calculus, is that you don't want to be sitting there going, okay, I have this 7-step procedure to run through. It's more of like, I see it, I don't have x-intercepts. I have a vertical, I have a horizontal. Here it is. Here's a quick sketch. Let me pick some test points. Let's see what this thing looks like. And it's something faster than what we've made it, if it's something simple like this. So let me pick my test points. I'm going to pick, how about 0? 0 is a good one. I only need 2 test points, don't I? 0 and 6. Plug them in. Plug in 0 into this and you get a negative number, right? So you're down. And if you plug in 6, you're positive. So draw your graph now. It's going to flatten out towards the magnet. It's going to dive down because of this vertical. On the right side, it's going to take off. And then it's going to flatten out over here. So where is this inequality true? Whenever the graph of that function is bigger than or equal to 0. Over here, right? Everything to the right of 5. So the solution to this inequality is x greater than 5, or if you'd like, we haven't done it that way, you could say parenthesis 5 to infinity. Sorry, I hadn't done that before, but interval notation like this. And we cannot include 5 because you have a vertical asymptote there. So that was good. That little combining, right? That really helped. Let me show you a different approach. Okay, that was perfect. I like that. But I want to show you a different approach. I'm going to ask you if this is okay. So what if you have a student do this? Or what if you do this? Is that okay? I just added 1 to both sides. Adding 1 to both sides of an inequality doesn't change anything. All right. Now I'm going to clear the fractions. I'm going to multiply this side by x minus 5. I'm going to multiply this side by x minus 5. They're going to cancel here. And I'm going to get x plus 1 greater than or equal to x minus 5. Okay. 1 times this is this. Now, this is a linear inequality. I'm going to subtract x on both sides. Uh-oh, what do I have? 1 is greater than or equal to negative 5. Is this true? Is 1 bigger than or equal to negative 5? It is. Which would give you the illusion, this would give you the illusion that this means this inequality is always true, regardless of what you ever plug in for x. And it's not. We know it's not true. We know it only works for x bigger than 5. Why did this not work? What's wrong with what I did? There's something very wrong with what I did. Okay, that canceling x minus 5. Why can I not do that? I can't multiply both sides of something. You're right, but why? Okay, it is. It's because it's not equal. And we're multiplying both sides by something, right? What if it's negative? What if I multiply? X minus 5 is something I don't know, right? So what if it's negative? What do I have to do? Flip the inequality, but I didn't know whether or not I had to or not, right? That was an invalid step. And that's why your answer is not correct, because you did something that wasn't valid. So there's danger. That's all I'm trying to get at, is there's danger in the algebra. Now, Juan at home said, let's get a common denominator. That's the way to go. You never want to start moving things over and multiplying by something where you don't have control over it, especially with inequalities, because things could flip and yeah, it gets messy. So, all right. So I think, unless there's anything else on this, I think I'm satisfied with this. Let's take a look at the I want to take a look real quick at the homework for this. I think what I'm going to do is give you some problems here out of here. I haven't even asked you all how you feel about not doing the homework on the computer, if you care or not. Where's the darn zoom on this thing? Wow. Zooming is a beta feature? Kind of weird. All right, so let's take a look at these. Solve each inequality. I'm going to grab this and I'm going to paste it into our notes, but I will send you this today. Okay. And I don't want you to do all of these, okay? I would say try and do, there's a lot of problems, right? 20, there's like, I don't know. I would say try to do maybe the odds, you know, see how it goes. See how it goes. Look at how these can be, some of these are simple, some of these are hard, right? Like these up here are polynomials. They're already factored for you, so you can like tell if you're bouncing or crossing. Y'all see that? Here. These, like this, you have to move everything over to one side first. So add 8x squared. Let me see, this is pretty straightforward. This is straightforward, I think. This is straightforward. They don't start getting interesting until you get to something like this. How would you do number 41? Okay, yeah, but you need to bring the 1 over, wouldn't you? So you need to subtract 1 to get it to be a 0 over here, and then you get a common denominator, right? What you don't do is multiply both sides by x minus 2. That's going to be trouble.
You want to set it to 0 before?
Yep, always get it to 0. Same with this one. Well, I'm not asking you to do 42. 43 though, same thing. You need to bring the 2 over and then get a common denominator. Bring the 1 over. Bring the 2 over. How about something, well, like this one, bring the 2 over. How about this? Or, yeah, number 40. Bring everything over, right? So bring everything to one side, get a common denominator, and then work it. Yeah, these will be interesting to see how you do on this. So try this, all the odds. Do you want to go through any of these, or do you all feel comfortable? Is there anything that you're looking at right there that you're like, might help if I see that worked? 51, does 51 look terrible to you? Yeah? You always pick the last one, the one that has the most stuff on it. It's actually, this one is not one of the harder ones. Let's see what happens. I will do it though. The reason why this one is not that bad is because everything's already moved over. Everything is, you know, less than 0. It's pretty much factored. The only thing I need to do here is figure out what the factoring of this is. See, this is already factored. This is already factored. Do y'all see this is like a rational function already factored out? So what is x cubed minus 1? Does that factor? Do y'all recognize that? If it was x squared minus 1, it would be a difference of squares, right? That's a difference of cubes. Do we have a formula for that? We do. All right, there is one. And as 14 students, let's make sure you know it. Okay, the formula is this: x cubed minus y cubed. The formula is that is equal to x minus y times x squared plus xy plus y squared. That is called the difference of cubes formula. There's another one, the different formula if you have a sum of cubes. And it's almost the exact same thing, except you have an x plus y here, then x squared minus xy and plus y squared. Anytime you're trying to factor difference or sum of cubes, yeah. I should mention one more thing about this formula. This formula turns a difference of cubes and factors it, right? Breaks it down to two things that multiply together. Do y'all see that this right here is a quadratic? This will never factor. Okay, what's left here will never factor. The reason why, well, the reason you know it will never factor is because if it ever did, then the formula would actually show you what this is factored. This is guaranteed to never factor. That's an important aspect of the difference of cubes and sum of cubes formulas. This will never factor, this will never factor. So for x cubed minus 1, what does x cubed minus 1 turn into according to this formula? What is it? So I have x cubed and minus 1 cubed, right? So y is 1. X minus 1. X times 1, which is just x, and then plus y squared, which is 1 squared, which is 1. Less than 0. Now it's factored, okay? Now I'm going to go through and see if I can't get a general idea of what this graph looks like. All right, so let's look at the numerator. This will give me x-intercepts. What makes this 0? If x is 3, right? So at 3, I have an x-intercept. All right, what makes this 0? Negative 1/2. Set that equal to 0, you get negative 1/2. Okay, 2 x-intercepts. How about vertical asymptotes? 1. And then I also need to know where this would be 0, right? And like I just said, it won't ever be 0. If it did factor, then they would have told, then the formula would have that. So this right here is what we consider to be prime. It will never be equal to 0. You can try for the rest of your life plugging numbers in here. It's never gonna be 0. In fact, if you look at it this way, this is a parabola, right? Just by itself. It doesn't have any x-intercepts, so it never hits the x-axis. So that's it. This is what we've got. We've got 2 x-intercepts. We've got 1 vertical, right? So now I'm not even going to worry about horizontals. I'm just going to go pick test points. Here, 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 here. And I got to plug those test points into this thing right here. So let me see. Test point maybe -1. 0 is a good test point. 2 is a good test point. 5 is a good test point. I'll start with 5. If I plug in 5 in here, 3 take away 5 would give me -2. I cube that, I get -8. So that's a negative number. 2 times 5 is 10 plus 1 is 11. So positive times negative is negative. Top is negative, right? Bottom, plug in 5, positive, and then 5 here would be positive. So what do we have? Negative over positive. So this is negative. So over here, I'm down. And then if you plug in 2, you should be up. And then you should be at 0. It should give you, is it up still? I think it's negative. It's negative. You'll get a positive on top and you'll get, there's a negative. Yeah, so you'll get down. And then at -1, you should be up. I didn't look at horizontals, but can you tell me whether or not it has any or not? Should not? Should not. Why? Yeah, if you were to expand this out, this would be x cubed in here. and this is x, so that should be like an x to the fourth. And then this down here, the max power you should have is x cubed. So that means the left side and right sides are either going to go up or down. When I draw this, it looks like this. Like that. And we want to know what? Where this thing is less than 0. That's happening here and here. So that's everything between -1/2 and what? 1, not including either one, right? Union, and then everything past 3.
It would be on the bottom half when it's 0, would it be actually like an x-intercept?
Where is that?
When it's less than 0, it's gonna be under the
Under the x-axis, that's right. If it would be less than or equal to 0, we would include that point, and we would include that point. But because they're not, we have open parentheses on the -1/2 and the 3. All right, so getting back to this, I think this is a good exercise. There's lots of problems to practice here, okay? See how you do with it, all right? Try the odds from there. All right. We have about 30 minutes left. I think that's enough time for me to at least introduce the next concept. Let's just say that this concept right here, from here on, like we're done. This is test material. This is it. What I start talking about now will not be on this test, only as a bonus. It would appear only as a bonus, okay? But we're going to talk about it now, and we're also going to talk about it on Wednesday, so just keep that in mind. That I'm done with test material. All right, so we are going to move to the next section, which is called function composition. So think back to when you were first learning arithmetic back in grade school, right? You're taught about numbers. And what was the first thing you were taught to do with numbers? Once you were taught, like, here's 1, 2, 3, 4, here are the numbers. What was the first thing? Add them up, right? So when it comes to numbers, right, when we talk about numbers, we have 4 arithmetic operations. Arithmetic, right? The 4 arithmetic operations are add, subtract, multiply, divide, right? And when we were back in grade school, we would do the multiply, we'd use an X, right? And we'd use that little division symbol, like in elementary school, we'd use multiplication, and then here we'd use that little division symbol, right? So the idea is that if you have any 2 numbers, right? Give me 2 numbers, I can always add them together, subtract them, multiply them, or divide them. And that's it. Those are the 4 operations. There's no other operation. How about exponents? What is an exponent? What is like 4 squared? That's multiplication, just repeated, right? So it is a version of multiplication. So those are the 4 arithmetic operations we have. Now, that's with numbers, right? Now, when it comes to functions, right? When it comes to functions, we also have the 4 arithmetic operations. The 4 arithmetic operations. So let me give you an example. I didn't give you an example of numbers because you all know how to add, subtract, multiply, and divide numbers. But when it comes to functions, we can do the 4 arithmetic operations with functions. So for example, if I give you, let's say I say, all right, everyone, I'm going to define a function f of x, and it's going to be the function x plus 2. I'm going to define a different function, g of x, and that's going to be the function 3x minus 4. And I want you to add the two functions together. Or I say, I want you to subtract the two, or I want you to multiply the two, or divide the two. There's a way we can do that, and there's notation for that. If I want you to add, what I would write is f plus g in parentheses of x. And all it simply means is to take the f function and add the g function, which means I would take x plus 2 and add 3x minus 4, combine like terms and get 4x minus 2. Meaning, if I now asked you to do f plus g of 2, that means you're just going to take 2 and plug it into this answer, right? So what would 2 be in here? 4 times 2 minus 2 would be 6, right? So plugging 2 into this function is equivalent to plugging 2 into both of these and adding them up, right? So what's 2 in here? 4, and what's 2 in here? Wait, 4. What'd you say? If I plug in 2 into here, I get 4. 2 into here, I get 2. 4 plus 2, 6, right? Same effect. So instead of working with, plugging something into here and then into here separately and adding them, this does it for us, right? And we can do that with subtraction, multiplication, right? Division. So the other notations we have, if we want to subtract, of course, it would be f minus g of x. Here, does the order matter? Yes, absolutely. F take away g is not the same as g take away f. I'm not going to go through this. Multiplication, the notation is f with g next to it of x, and that just means you take the f function and multiply the g function together. And the last notation we have is division. And that means you write f over g of x. And that means you take the f function and you divide the g function. So back in grade school, to give you numbers, they tell you these are the 4 arithmetic operations. You go play with numbers. Then you're given functions. You're said, hey, here's some functions. Here are the 4 arithmetic operations. Here's how you do them, right? We should all be somewhat comfortable with those. With functions, however, there is a 5th operation that you don't have with numbers. There's something you can do with functions that you can't do with numbers, and it's called composition. You can compose 2 functions, but you cannot compose 2 numbers. So we need to understand what it is first. So composition works like this. Let's say that we have 2 functions. We're given 2 functions. F and G. And I want to compose them together. Here's what I'd like for us to do. I'd like for us to imagine we're going to take some value of x. We're going to take that value and we're going to plug it into the g function. Now the g, if you give g a number, it's going to spit out an answer, right? Whatever g is, you hand it a number, it's going to spit out some answer. That should be g of x. What I want you to do is then take that answer that you just got, and I want you to send that through the f function. The f function should take that in and spit something new out, shouldn't it? It should spit out whatever f is when you plug g into it. This is what composition is about. Numbers don't behave this way, all right? I can't ask you to take the number 3 and compose it with the number 4. It doesn't make any sense with numbers. With functions, you can, because functions are like little machines. You have an input, goes in through G, comes out as an output. That output can now become the input of F. And that can come out at the end of this. It's like a chain of events, right? Now, I chose to plug the X into G first, right? Could I plug the X into F first? I mean, you're free to do whatever you want, okay? That's a different composition though. You start with X, send it through F, that'll come out F of X. And then take that answer, send it through G, and it comes out over here as G with F X. So this is where I like to play a little game. It's not a fun game, so don't get excited because it's not fun. We're going to have two groups in the class here, all right? We're going to have the F's and the G's. So the F functions, y'all are going to be X plus, what was the function before? X plus 2. We're going to make these real simple functions, okay? X plus 2, the G's, y'all are going to be 4X, okay? So let's let over here, these three here, the three in black here, kind of dark tops. Y'all are F, okay? Y'all are X plus 2. Whatever we hand you, you add 2, right? Everyone else, y'all are G. Whatever we hand you, you spit out 4 times that, right? Okay, so I get to control X. So I'm going to take X, I'm going to pick 3. 3, I want to send it through F. 5, you send that to G. 20, right? That's composition. The number went in, it went into F first, then it went to G, right? Let's do it the other way around. What number did I give you? 5? Okay, now, no, it was 3. Y'all split out 5. So now let me do it the other way. If I plug in 3 into G, what do you get? 12 goes in here. 14. Do y'all see that doing it that way, it didn't give you the same answer as the other way? Like it mattered. So composition doesn't in general commute. You can't flip the order and it stay the same. That makes sense? Okay, let's do this. I want to send a number through F twice. Okay, so I'm going to give you all 3. Send it through 1 time. 5, send it back through. 7, okay? Composition, you can compose a function with itself. It doesn't have to be 2 different functions composed. You can have it go through the machine twice, 3 times, 4 times. So let's do this. Let's see if y'all can keep track of this. I would like to send 3 through twice here, okay? Y'all give that answer to them and send it through you 3 times. Got it? Okay, so here comes 3 into you. 12 and then 48, and that goes through you guys. 50, 52, 54. Do y'all see? Like, there is no limit as to how big the chain of compositions has to be. There's no rule that says you can't do the composition repeatedly on the same function. We could go crazy. We could be like, go through F to G, back to F to G, to back to F to G, do it 100 times. What's the answer, right? There's no restrictions, but it's so unique to functions that you can't do with anything else. So there are these certain functions in math that are very special where, well, yeah, I'm not going to go there. All right. So notation, this right here, this idea of this chain of events, X goes into G, then it goes into F, or you could have X go into F and then into G. And then in reality, you can make this look however you want to look, right? However, so we need some notation to kind of help you to understand how I want the chain to go. So if I write this down, new idea here. If I write F with a little O next to it and then G, that is the notation that we use to let you know we're doing composition. This is not multiplication, right? This is not addition or subtraction. It's a little O there. And that's what we use for composition. So F of G is the way we'd write, the way we would say this is F of G of X. That's the way we verbally say that. f of g of x. And what that means is this. You're going to have the f function, and inside of it, you have the g function. So my question to you is, with that notation, which function gets x first? G, right? Do y'all see that from that notation? The x goes into the g, and then that answer goes into the f. So that would be me saying 2 goes, or sorry, if I tell you plug in 3 here, y'all were g, right? It would be 3 into there and then to you guys. That's that. Now, if I switch the order and I do it this way, g little o of f, g of f of x, then that means g is on the outside, f of x is on the inside. So x goes to f first. That's this direction through the room. So we go around through f, and then that answer goes into g. Making sense? A lot of times students will come to me and they'll be like, yeah, I learned this in high school. We called it fog and goff. I don't know if you've ever heard that before, fog and goff. That's cute, whatever, if you like that. But the problem with fog and goff to me is that that makes students think that's the only thing you can do. They are very important, but it's not the only thing you can do. So we could have this. How about fagog? What would fagog be? You know? So who do you think gets x first here? G gets it first. And what does that answer get put inside? G again. And then what does that answer get put into? F, you see? So I like to look at this notation as like, you're working almost from right to left. X goes into G, that answer goes into G, that answer goes into F. And there's, like I said, there's no limit on how many of these you can have. And you can do this with more than just 2 functions too. You could have 3 functions, f, g, and h, and then anything you could think of to compose them together would work. Why is this important? Well, there's so many different reasons of it, why this is important. At this level in this class, we want to just be able to do it mechanically first, understand how to do the mechanics of it. And then next class, what we're going to do is we're going to talk about how we can use this to prove that a function has an inverse, which is a function that undoes it. And then we're going to see how in calculus, we actually need this. My students are currently suffering right now through a thing in calculus 1 called the chain rule. And a chain rule is a difficult thing to get your head around, but your understanding of composition makes it much easier. If you don't understand composition, chain rule is very difficult to understand. So, all right. So let me do this. I'm going to give you a couple of functions. F of x equals, let's go with x plus 2. Let's do g of x is x plus 3 over x minus 1. And let's do h of x is 5x. I'm actually giving you specific examples of functions right now. First things first. Find f of h of x. So x goes into what first? H, and then that's going to go into f, right? So I'm first going to write the notation down. F, inside of that goes h of x. Now, I know what h of x is, don't I? H of x is 5x. So I'm going to do f, and I'm going to replace h of x with 5x. That's just replacing that with what it is. Now, what happens if I take 5x and plug it into f? So I replace that x with 5x. What would this become? 5x plus 2. And see, there's no more f here, right? You see that the f is gone? Because I've actually taken this and plugged it into the function f. And so this is what it spits out. What's nice about this answer is that this actually does the chain of events for you, right? Like you don't have to worry about h getting it and then F. This is the end result of the two of them together. So let's just check it. If I plug 1 into H, what would happen? 5. And then if I take that answer 5 and plug it into F, I get 7. Well, that's the same as plugging 1 into this. You get 7. Let me give you another one. What is G, the second one, G of F of X? This one's a harder one. G of F of X. So by definition, this is G with inside of it F, right? And F of X is X plus 2, right? And now we've got to take that X plus 2 and evaluate G at this value. That means we're going to replace wherever we see an X in the original G function, wherever we see X, we're replacing it with X plus 2, right? So what does that become? I'm going to go a little slower. X plus 2 plus 3 over X plus 2 minus 1. See, I'm replacing this. X plus 2 is going here and here. There and there. And again, no more G, right? G is not written anymore because we've done G. This has now gone through G. Simplifying that, you said was X plus 5 and then X plus 1. There you go. That is the composition. I have a question now. This will be the last thing we talk about. I'm not going to do another example. I'll save this for next class. I have a question. Right now, for this problem, right, we have that G of F of X is equal to X plus 5 over X plus 1, right? Okay. What is the domain of that function? What can you not plug in? -1, right? Can you all tell just by looking at this, you can't plug in -1? I agree, all right? Can't plug in -1. Now, let's see why you can't plug in -1. Look at the G function. Right now, we're looking at just G and F, right? I'm just going to scratch out H for now. Look at the G function by itself. Can you plug -1 into this? Yes. Can you plug -1 into this? Yes. But so by itself, F does not have a problem with -1. By itself, G does not have a problem with -1. But when you compose the two together, there is a problem with -1, right? Domains of compositions are a little tricky. This one is obvious because we can just see it right here. So next class, what we're going to be doing is we're going to be doing more complicated ones. And we're going to have to see that when it comes to domains, we're going to have to we're going to have to solve an equation because there's this like intermediate step where, like, let's say you have X is going to go through, let's say X goes into G first, then goes through F. F already might have some domain restrictions, right? Like maybe you can't plug 2 into this, right? So maybe F is some function where I can't plug in 2. Well, what if I plug in an X here and it spits out 2? I have trouble, don't I? So we're going to have to figure out what X is here would cause a 2 to come out. And we need to eliminate that from our input. So it's going to get more complicated. This was just to give you kind of a preview into composition. We'll come back next time. We'll get into a little more detail. For now, focus on your homework for the inequalities. Yes?
Is it the reason why it can't be -1 on the denominator is because we can't have 0?
That's right. Can't, yeah, if we tried to plug -1 into this, we would get division by 0. All right, everyone, have a good rest of your day. Thank you for your attendance. Again, the test will be next week on Monday, a week from today. All right. Tavi, I'm not sure what you were talking about, 35, 41, 21. What are you referring to?
Oh, it was for the questions that you told us to work through, either do the odd problems or not.
Oh, why were they highlighted? Oh, these mean, I believe that they correspond to a problem in the textbook that's worked out as an example or something like that. I think in the examples in the book, they tell you, hey, now try this one. And it corresponds to these problems.
Okay.
Yeah,
All right.
you don't need to worry about that.
Okay, thank you.
All right, no problem.
All right, sir. Have a good day.
You too. Thank you.